Okay, so this is the last lecture in which we will essentially be studying the combinatorics of the boundary of the Deligne-Mumford compactification. And we'll see that we've done most of the work already in the last few lectures. So in other words, I'm going to identify the tropical moduli space with the boundary complex of the toroidal embedding, MGN inside MGN bar. And with the remaining time, I'll discuss some applications to the topology of MGN using this combinatorial reframing. Okay, so last time we discussed toroidal embeddings of varieties, and this time I want to tell you that the same theory applies to the theory Deligne-Mumford stacks. And I will not actually, I know that these objects have come up in previous courses, and I'm going to just go through it again anyways. I will have to omit many details, but I'll try to give you a sense for exactly what I'm skipping, and I hope to convince you that the theory of toroidal embeddings and their boundary complexes carries through without significant technical changes to the case of stacks. Okay, so if it's okay, let's fix an algebraically closed field K, and I'll write schemes sub K for the category of K schemes. And you've probably seen that there's no fine moduli space of stable genus G and marked curves, in the sense that there's no space such that morphisms from a scheme S to that space precisely encode families of curves over S. So let us nevertheless sort of axiomatize into a category the properties that we want. And this is the category that I'll write MGN. So this is what I mean for the moment by MGN. This is the category whose objects are, well, families. So let's say F from X to B. This is a flat proper morphism of schemes of over K. So this is a morphism in K schemes. And then, of course, we have sections, P1 through Pn, from B up to X, such that the geometric fibers are stable curves of genus G. So the geometric fibers are stable genus G and marked curves. Sorry. Okay, MGN, the geometric fibers are smooth genus G and marked curves. And this definition can be repeated for the case MGN bar. So the category MGN bar has families, has objects that are just families of stable curves. So that's what I mean by MGN and MGN bar. Now, these categories come with natural morphisms, natural transformations to the category of K schemes, where you take one of these families and you just remember the base scheme. So let's just recall that. So we have morphisms. Which are sort of the obvious morphisms from MGN or MGN bar, taking a family to its base. Okay, and this is what we mean by a category over the category of K schemes. So MGN and MGN bar are categories over the category of K schemes. So they're equipped with this functor back to K schemes that just remembers the base. And these are examples of categories fibered in groupoids. or CFG for short. Okay, so a category fibered in groupoids is a category over your base scheme, schemes over K, satisfying some additional properties that I won't write down precisely. So those additional properties in this case amount to the requirement that pullbacks of families exist and are unique up to unique isomorphism. Oh, I guess I didn't even say what my morphisms are. I'm really sorry. Okay, so morphisms are Cartesian diagrams. So pullbacks of families of curves. Okay, along with the pullbacks of the sections in the appropriate way, which I'm going to drop from the notation. I hope that's okay. So morphisms are pullbacks, and these categories are fibered in groupoids, which amounts to the thing that you know about pullbacks, which is that they exist and are unique up to unique isomorphism. Okay. Another example of a category fibered in groupoids is obtained by taking any scheme whatsoever. So any scheme in our, so any scheme over K defines another category over K schemes, which I claim is fibered in groupoids. And I'll denote it S underline. And the objects of S underline are just schemes over S. So the objects are morphisms X to S of K schemes, and the morphisms are commuting triangles, X prime to X down to S. And this is certainly a category over the category of K schemes, and I claim that it's fibered in groupoids, which in this setting amounts to checking that compositions now, not pullbacks, but literal compositions of morphisms exist and are unique. Okay, so this is the setting in which we're treating MGN and MGN bar. Is it okay? All right, now I will have to fast forward a lot. Oh, so maybe, sorry, before I do that, let me just say that a morphism of CFGs is just what you think it is. It's just a natural transformation, so it's a functor. Say F from C to D, where these are categories fibered in groupoids, and it is a functor that respects the structure morphism down to the category of K schemes. So such that we have a commuting triangle of functors. So this is down to K schemes here. Okay, so this is an exercise which you've probably done already, maybe in slightly different language, but the exercise is that to give a morphism, say, from S underline to MGN, is to give a family of stable curves over S. So this is the usual Yoneda correspondence, which I'll call an exercise. You've probably seen it. All I'm saying is that this category operates in the way that we want, as if it were a fine moduli space. So the exercise is to make this precise and prove it, that the data of a morphism from S underline to MGN, or similarly MGN bar, is the data of a family of curves of type, GN over S. Okay, and you've probably done this already, maybe in some slightly different language, if not this exact check. Okay, so that's the way in which we're treating MGN and MGN bar. So now, I'd like to fast forward through a lot of theory, because I can't build my way all the way up to the definition of a Deligne-Mumford stack. So let me just tell you the basic properties that I need the philosophy, by the way, is as follows. So you can see that through this example, our categories, fibered, and groupoids generalize. But they certainly include the theory of schemes, and in fact, they generalize the theory of schemes in the sense that not all CFGs are of the form S underline for some scheme S. So stacks, and in particular, Deligne-Mumford stacks, are CFGs that satisfy some extra geometric type conditions. So they satisfy some extra conditions. And those conditions sort of ensure that the resulting objects behave a little more geometrically. They sort of behave almost as if they were schemes, even though they're not schemes on the nose. So let me not give the full definitions, but I'll write some facts, namely some properties that Deligne-Mumford stacks do enjoy. And these are geometric properties that we'll make use of to be able to just pull over the definition of toroidal embeddings almost word for word to the category of Deligne-Mumford stacks. Okay, so I need to fast forward through many details, as I said. So Deligne-Mumford, so I'll just say that stacks, and even more especially Deligne-Mumford stacks, they are CFGs, so they are categories over schemes, fibered and groupoids, with some extra properties. And I'll state now two properties of Deligne-Mumford stacks that I need, and I'll ask you to accept them if it happens to be the case that you've never seen these definitions. Okay, so first, so here, I'm going to talk about Deligne-Mumford stacks. So, right, so if I have Deligne-Mumford stack M, then one of its properties, this is one of the requirements to be a Deligne-Mumford stack, is that it's representable. So this means, let me say it in the following way. So I'll say just what I need. So there exists, so for every scheme S with a morphism to M, so let's call this little f, and for every scheme T with a morphism to M called G. So here I'm mixing, sort of on purpose, the language of schemes and their associated categories, fibered and groupoids. Okay, so, but we think of it as having a morphism from a scheme S to M and a scheme T to M, then the property or the requirement is that the fiber product, S product with T over M, which I will not define, so there is a notion of fiber product. So I won't define it. I guess I shouldn't write that it's not defined. It is defined, but I'm not going to do it now. So the fiber product is, well, it exists, and it is a scheme over K. And this is sort of like the crucial property that allows us to treat M as if it were a scheme. For example, we'll say that a morphism from a scheme S to M has some property P, where P is like any of your favorite properties of morphisms that's preserved by base change. We'll say that this morphism of CFGs has property P if whenever you pull it back by a morphism from a scheme T, you get an actual honest morphism of schemes with that property. Let me write that. So for any property P that's sort of reasonable, that's stable under base change, so a property of a morphism, right? If M is a Deligne-Mumford stack, then we'll simply say that F from S to M, where S is a scheme, has P if whenever you pull it back to the fiber product. So for this morphism, which is an actual morphism of schemes from S cross T over M to T, we ask that this is, which is a morphism of schemes, which you understand now, is a morphism with property P. Okay, is it okay? Okay, so the second property of Deligne-Mumford stacks is that there exists an étal surjective morphism. In other words, an étal cover.
So
Yeah.
I don't really understand. I mean, for any property P, so you want that this is verified for every T, right? This.
Yeah.
Okay.
Uh-huh.
Okay.
Oh, I see. Okay, yes, absolutely. So let me, I'm about to do an example in which the property P I am interested in is the étal property. Yeah, okay, so a property, a requirement of being a Deligne-Mumford stack is that there exists an étal surjective morphism from a scheme. So here U is a scheme. Right, so as pointed out, again, what I mean here is that whenever you pull back the whole thing by some morphism from some scheme to M, you get an étal map of honest schemes. Okay, and this is the key property for us. I mean, so like very roughly, this is a property that says that M is somewhat geometric. Locally, everywhere at M, it has a quote-unquote scheme finite covering space. Very roughly, that's the, I guess, some very rough intuition. And this is the property that will allow us to just repeat the definition of boundary complexes of toroidal Deligne-Mumford stacks. Let me say what toroidal is, right? I owe you that definition. So, definition. Oh, sorry. So before that, let me just say, let me get rid of a bunch of pathology. So let me say that all the stacks that I'm considering, so I'll be considering Deligne-Mumford stacks, and all of them will be separated and connected. Sorry, this is not a property of all of them. The ones that I'm considering are separated and connected. So definition now. Suppose we have U inside X. This is an open substack of Deligne-Mumford stack. Okay, so what does open substack mean? Well, it's just like an open subscheme. And I mean that literally. I mean it in the sense of using pullbacks to schemes to define properties of morphisms. Okay, so you have an open substack inside a Deligne-Mumford stack. And we say that this is a toroidal embedding. Of Deligne-Mumford stacks if for every étal morphism let's call it V, yeah. So if for every étal morphism from a scheme the morphism of schemes obtained by taking U and pulling it back to V by the étal cover. So this is U fiber product over X with V going into V is now a toroidal embedding in the previous sense, the sense that we discussed at length yesterday. Okay, so basically, up to passing to étal covers, we have a toroidal embedding of schemes. That's all. Is it okay? Okay, so I will now define the boundary complex for you. Actually, I don't really have to do it. I'll just write out the same definition as from yesterday. And then we'll discuss at length the key example, which is MGN bar, which is a Deligne-Mumford stack which admits a MGN as a toroidal open substack. Okay, so let me do those things. So boundary complexes are now defined in just the same way as before. So again, we follow Thuillet's definition, and I'll attribute to Abramovich, Caparasso, and Payne the fact that all the theory works out the same way for stacks. Okay, so boundary complexes of toroidal Deligne-Mumford stacks. So again, we have U inside X, such a toroidal embedding. And then we just define boundary complexes in the same way. So we take V to be an étal cover of X. So an étal surjective morphism, such that the pullback, oh, you know what, maybe to be consistent, let me write D for the complement of U. Okay, so we take, right, so we take, you know, okay, sorry. Let me continue with what I was doing. So the whole point is that we just take an étal cover such that we recover a toroidal embedding now of varieties without self-intersection, just as in the schemes case. Sorry about that. So we let V to X be an étal cover such that U fiber product with V over X into V is a toroidal embedding of schemes now without self-intersection. And this can always be achieved. Okay, so let me write U sub V for this open subscheme of V. And let me write D now, D sub V for V minus U sub V. And then just as before, we define the boundary complex of U inside X to be the co-equalizer of the appropriate diagram. So this is the boundary complex of V2 going to the boundary complex of V, where, as before, right, so as before, V2 is the fiber product of V and V over the stack X, but V2 is just a scheme again by property number 1 of Deligne-Mumford stacks. So this is just a scheme, and we have a divisor, D2, which is dV cross dV over X. This is as before. So again, D2 inside V2 somehow gives you the gluing data that allows you to pass from the boundary complex of your étal cover to the boundary complex of your original toroidal embedding of Deligne-Mumford stacks. And the construction goes just as before. So this is the co-equalizer in, again, the category of topological spaces.
I'm sorry, could you remind us what the co-equalizer means?
Just co-limit. Okay, so yes. So you have two morphisms of topological spaces. So just please glue points that are obtained from this identification, right? So consider as an identification of topological spaces. No, that didn't help, sorry. Okay, so yeah, so if you have some diagram of topological spaces, then that diagram, we say that a topological space is a colimit of that diagram if it admits all morphisms, sorry. So if there are morphisms to that colimit from each of these topological spaces that commute with the arrows, and furthermore this initial with respect to that property. So it's just gluing. Gluing of topological spaces according to the appropriate quotient obtained by using these two arrows as an identification. Was that worse? I can't tell. Are you guys, it was worse. Uh-oh. Sorry? It's okay? Okay, 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 great. Okay, thank you for asking. Anything else? All right. So we're in the situation where we get combinatorics associated to toroidal embeddings of Deligne-Mumford stacks. And I want now to talk about the case of MGN inside MGN bar for the remaining time in the lecture. And I'll state this as a fact, but of course, lots of brilliant mathematics went into this fact. MGN inside MGN bar, the Deligne-Mumford-Knudsen compactification by stable curves, is a toroidal embedding. Of Deligne-Mumford stacks. Indeed, it's a normal crossings embedding. So the boundary MGN bar minus MGN is normal crossings. Though it's very far from being simple normal crossings. So we're really going to have to use this sort of more technical definition of a boundary complex to deal with the boundary. So it's not at all simple normal crossings. And moreover, as you're probably aware, MGN bar is smooth and proper. All right, I'm quickly getting into the portion of my talk where I can't really define anything close to rigorously. I guess I already got there before, because I haven't told you precisely what a Deligne-Mumford stack is. Nevertheless, I'll try to give you a sense for how these things work. So I'll state for you, I think we discussed this, that the boundary, which is normal crossings of MGN bar, has a natural stratification. And the strata of those, right, so this is a stratification according to its structure as a normal crossings divisor. And the strata are in bijection with combinatorial types of type Gn. Okay, so we're going to discuss now the individual boundary strata, and then we'll discuss sort of the way in which the local combinatorics patches together into the full boundary complex of this toroidal embedding. All right, so the boundary strata of MGN bar. Okay, so let's fix. Right, okay, so first of all, let me say the strata are naturally indexed. By combinatorial types, or in other words, weighted marked graphs. Of type Gn. Genus G and n marked. And this is not some like mysterious indexing. I just mean that the strata are moduli spaces for stable curves of a fixed dual graph. Is that okay? So let's describe them. So let me fix, I'll write bold G just for short, for such a combinatorial type, so a vertex-weighted, n-marked graph. And we'll describe the stratum, which I'll write M sub G, corresponding to G. So it is a moduli space, again, for those stable curves with dual graph G. And this description you can find in the textbook ACGH. Arborello, Cornalba, Griffith, and Harris. Okay. So here's the deal. Wait, did I get this reference wrong? It might be ACG.
Right.
Okay, ACG 2, the second volume, that's what I mean. Sorry. Okay, so the idea is simple. I mean, proving it is a different thing, but the idea we can describe from first principles. So let's let, first of all, for each vertex of the dual graph, let me let n sub b be the number of marked points at v plus the number of half edges at v. So the number of special points, in other words, marked on the irreducible component corresponding to v. So the number of marked points plus the number of half edges at v. So this is some number. And now let me let, as an interim, let me let M sub G tilde be the product over all vertices of the spaces M, no bar, right? So just M sub weight of V, comma, N sub V. So I'm basically trying to go component by component in terms of building a stable curve of type Gn. For each component, I pick out a curve of the correct genus, which is indexed by, corresponding to the weight of that vertex. And I have to mark some special points on it, either the actual marked points or the points of eventual attachment to other components. So if you think about this, this parameterizes, so this is a moduli space. So Mg tilde is a moduli space for stable curves of type Gn, stable n-marked genus G curves, together with some rigidifying data, namely, together with specified a fixed isomorphism from the dual graph of that stable curve to G. In other words, these combinatorial types come with automorphisms. I don't know if I defined this too carefully, but there's, actually I did. I defined some category of stable n-marked graphs, and so I'm talking about the isomorphisms inside that category. And those automorphisms of G, if you believe this interpretation, act in a natural way on M tilde G, and the stack quotient is the thing we want. So I guess the theorem is that the stratum of MGN bar corresponding to stable curves of type G is obtained by a canonical identification by taking the stack quotient Mg tilde, as described just previously, by the action of the automorphism of the type G. And now I propose to do an example very explicitly and very slowly. I hope that's okay. Sorry, is this statement, though, is it clear? Or are there questions? Okay, yeah? Okay, so let's do an example. All right, I'm going to take a stratum in M13 bar. So let's let G be this combinatorial type, which I'll draw for you. So 2 vertices, 2 edges, and 3 marked points in this arrangement. Okay, so algebraic geometers more typically draw the combinatorics of the stratum in the following way. And earlier in my course, I've also been drawing this in this sort of fake complex analytic picture. So something like this. Okay? All right, so we're interested in parametrizing, in a strong sense, the stable curves with this dual graph. So how do you make such a stable curve? Well, according to what we just said, we'll do it in pieces. We'll look at the component on the left and the component on the right. Now, the component on the left amounts to a choice of 3 distinguished points on a P1, and the component on the right amounts to a choice of 4 distinguished points on a P1. Right? So with some rigidifying data, the stack mg tilde is just M03 cross M04. Is it okay? Yeah. Okay. Right, so again, so you pick 3 points on a P1, and then you pick 4 points on a separate P1. And then you have some specified identification in mind already that transforms that data into a particular stable curve. Okay, now, note that the automorphism group of this graph is Z mod 2Z. Right, so there's a flip of these 2 edges. And that corresponds to the fact that if you tell me like 4 points on a P1, say Q1, Q2, Q3, and Q4, and you say, you know, let me actually get it consistent. You say that the first 2 are going to be the marked points, and the last 2 are going to be attached to another P1. Then you've overspecified because an involution of 2 points specifies the same stable curve. That's the Z mod 2Z involution that we're modding out by. So again, we have this automorphism group acting naturally on our 2 moduli, the product of our 2 moduli spaces. And this action is not mysterious at all. We've studied these moduli spaces, I think, many times over the course of the last 2 weeks. So this is just a variety, right? It's just a variety. This is a point. And this, after the usual projective changes of coordinates that take your first 3 points to 0, 1, and infinity, this you can identify with, right, so this is point cross P1 minus 0, 1, and infinity, for example. Okay, and the automorphism is the one that says, let's see, that we'd like to identify say the ordered collection of points 0, 1, infinity A, where A is some parameter for this space, with 0, 1, A infinity. So, right, so with the understanding that I'm telling you my stable curve by just telling you marked points like this, with the understanding that I'm about to glue A and infinity to another P1. So we have to mod out by this involution. And in order to do that explicitly, which I'm going to do for you, we'll note that by a projective change of coordinates, this latter quadruple of points can be taken to something of the form 0, 1, infinity, something. And I calculated that something. I believe it's 1 minus a. So you can do that, certainly, by elementary projective geometry. So let's identify now completely explicitly what this stratum really is. Yeah, was there a question? Yeah.
Instead of M13, we had M12. There was an automorphism of the graph.
Yeah.
That doesn't have any effect on the curve because the switching the edges doesn't have any effect. I mean, it's the same curve. What does it mean?
This kind of thing
No,
with the loop? Sorry.
The two component, 2p1,
Yeah?
is actually 2 point with one market point on every p1.
Okay, let me try to draw what you're saying so I can understand your question.
Yeah,
This kind of picture.
Yeah, this one.
Okay, there's no such involution because these are marked points, right? So I'm only interested in automorphisms that fix pointwise the marked points. Okay, so what is a stable curve? What is an automorphism of a stable curve? It's an automorphism of the underlying curve that fixes the pi's pointwise. So this is just a point. Right, so let me draw the dual graph. Yeah, thanks for asking. Yeah. So there's no automorphism switching the 1 and 2. Oh, are you concerned about the other automorphism? Yeah, totally, yeah.
The other automorphism has trivial action on the step. That's right.
No.
The other automorphism, the one switching the edges on the graph.
Oh, sorry, yeah. Sorry. So you're talking about this automorphism, which identifies these 2 points like that, right?
Yeah.
Yeah.
That's trivial action. I mean, I think what I'm asking is this action, this quotient you write up is not faithful. I mean, the action is not always faithful.
Okay. So it should be, right? So, okay, so let's look at the combinatorics of this stratum. It should be a cone modulo symmetries, right? So okay, so suppose you want to so suppose you want to tell me a point in this stratum, right? So you say something in M03 cross M03, so that's a point. And then the quotient is a point mod z mod 2z. So it's a stacky point, right? Yeah. So I basically think that this is going to be subsumed in the slightly bigger example that I'm giving. So maybe let me finish the example and then you can complain about it. If it's maybe I'm off by z mod 2z, but I don't think so. So yeah, so this should again be a stacky point. All right. Okay, so where was I? Okay, so what is this stratum ultimately? So my stratum, MG, is canonically isomorphic to, again, it's a P1 minus 3 points. Quotienting by the relation that sends a coordinate A on this variety to 1 minus A. And I take, again, it's not the scheme quotient, but the stat quotient. So maybe let me try to draw this. I will make an attempt. So this is going to be sort of, okay, so let me draw the space upstairs with in a picture that suggests the quotient action. Okay, so downstairs we have a punctured P1. So so we take out the point at infinity, and we take out a point that corresponds to 0 and 1 upstairs. So we have 2 sheets upstairs that are punctured at 0 and 1. And this cover is like 2 to 1 everywhere except over the point 1/2. So A equals 1/2. So here we have, yeah, okay, this is a little hard to draw, sorry. So I have some double cover here. This is, okay, what is this picture? This is supposed to be my P1 minus 3 points. So infinity's gone, these are 0 and 1. And then down here is I'm trying to draw a picture of the stack quotient. At the moment, I've only drawn sort of the scheme quotient, and that's not good enough. The stack quotient is just like the scheme quotient, but over at this point, marked A equals 1/2, which has a stabilizer, we have somehow a Z mod 2Z stacky point right there. Okay, so that's my picture of the stratum. Is that okay? Okay, good. So yeah, so I'm going to have to omit even more details at the moment. But this gives you a picture of the local, like, right, so this is a picture of the stratum corresponding to my dual graph here. And you can see now the way in which it's reasonable to associate the cone, so the two-dimensional orthant modulo flip, with this stratum. So it is, in fact, the self-intersection of the boundary divisor, right? So M sub this guy is, right, so locally here, along this stratum, we have 2 analytic branches. Obtained by contracting either of the 2 edges. Which happens to produce the same combinatorial type twice. So what I'm saying is that there's a boundary divisor corresponding to this graph, and that boundary divisor is a dimension 2 thing inside this moduli space, and its intersection is this dimension 1 stratum, so it's a self-intersection, so to speak. And furthermore, this self-intersection has the structure that we have seen yesterday from the example of the Whitney umbrella. So what I'm saying is that, like, the analytic branches are indistinguishable in the sense that if you take a path, so if you're sitting, I don't know, okay, right, so approximately we have this picture. Okay, so this is like just a totally inaccurate cartoon of 2 analytic branches coming together along the one-dimensional stratum that I've drawn in 2 different ways. One way that algebraic geometers would be more likely to draw it, and here is an attempt to draw it as if we were over C. Okay, anyways, the point is that this behavior that we're seeing of the indistinguishability of the 2 analytic branches is exactly as we saw in the Whitney umbrella. Here, the stacky point, so this puncture is sort of irrelevant. It corresponds to an even smaller stratum. This stacky point is playing the role of the puncture of the Whitney umbrella pole in yesterday's talk. In other words, if you take your parameter A and you start walking around in a loop, you'll see that the branches of the divisor that you're sort of locally viewing as you walk around the loop are interchanged. So it's monodromy with respect now to a Z mod 2Z stacky point. Okay, so it's the same behavior as yesterday. All right. So let me say quickly now that all of this can be put together in the following way. So I'll unfortunately just have to state this very loosely as a fact. Okay, so it is in fact a fact, but I probably won't have time to say it in a sufficiently detailed manner. All right, so so the point is that, sorry. So we have, for every p, let's write it this way. So given a point P in MG, corresponding to a stable curve C, or yeah, let's just say C for the moment, with the marked points suppressed in the notation just for the moment. You can describe fairly explicitly a local, like a neighborhood of P, an étal neighborhood of P. And it's just sort of the deformation space of the various nodes. So let me write, there is an étal neighborhood of P, right? So some étal map of schemes covering like a neighborhood of P. So this neighborhood has the property that the boundary, the image of the boundary of MGN bar can be identified locally, like étal or analytically locally, with n hyperplanes. Sorry, so I'm just trying to say to you right now that like there's a very explicit way to understand the normal crossing structure of the boundary complex, of the boundary of MGN bar. And the normal crossing structure precisely comes from looking at all ways to contract all but one edge of your dual graph. In other words, you see for every edge in the dual graph a coordinate hyperplane in the device, in the boundary. So, in which the boundary of MGN bar is a union of irreducible divisors intersecting transversely, so with simple normal crossings. And these boundary divisors correspond to sort of parameter spaces for smoothings of each individual node in the stable curve. So corresponding to, so parameter spaces for smoothings of the nodes. Okay, so maybe I'll refer you to the previous cartoon of what it looks like to be at a point in the one-dimensional stratum we've been discussing. So the claim is that there's an étal neighborhood in which the boundary precisely parametrizes the ways to smooth the two individual nodes. And those smoothing spaces intersect transversely. And that's a true statement when you pass to an appropriate étal neighborhood. So what I'm saying is that the boundary complex of this neighborhood of P is just a simplex, right? It's the boundary complex associated to something that locally looks, something that looks like the intersection of coordinate hyperplanes. It's a simplex of the appropriate dimension, e to the g, e of g minus 1. And it furthermore turns out that this notion of monodromy that we've been discussing is evinced in the boundary complex of VP cross VP. So this boundary complex, with its two maps to the boundary complex of VP, identifies like the coequalizer. So the coequalizer is naturally identified then with the orthant, sorry, so this is the simplex, rather, modulo the automorphism group of G, as is reasonable, at least on an intuitive level. So the automorphism group of G allows you to tell which of the branches are sort of indistinguishable, up to monodromy of the relevant stratum. And again, that monodromy I'm using at the moment in a loose sense. It includes possible monodromy on zero-dimensional strata. So points can have monodromy in the stack theoretic sense, if the point is, say, a point mod G. Okay. So I'll now, having said that very roughly, I'll just state that you can put all of these pieces together to make the desired identification that I've been alluding to of the boundary complex of MGN bar, which is built from things of this sort, with the tropical moduli space, the link of the tropical moduli space. So, theorem. Yeah?
When you write the smoothing of the nodes, you mean that
Sorry?
You have your normal crossing divisor,
Yeah.
and you perform an étal cover to have a simple normal crossing divisor.
I've already done that. So I'm saying, like, I'm working in some étal neighborhood where I have locally a simple normal crossing divisor.
I mean,
Yeah.
this operation,
Mhm.
it's a geometric operation of resolving the singularity, of smoothing the node.
No, what I'm saying rather is that I'm describing a parameter space, so an étal neighborhood of a point P in the moduli space. And the divisor pulls back, so the boundary divisor of MGN bar pulls back to what looks like an intersection, a union of coordinate hyperplanes. Now, each of those hyperplanes is the space of smoothings for a given node of the stable curve. That's what I'm saying. So as you walk along, say, if you walk into one of these coordinate hyperplanes, what you're doing is telling me how to smooth a node and pass to a boundary component of higher dimension. Yeah?
May I make a remark?
Yeah.
Because this is related to the question you made before.
Mm-hmm.
The graph, the
Yeah.
homomorphism of the graph is not the one which changes 2 with 3, but it's exactly the one which changes the 2 nodes.
Correct. So the automorphism
Which
here,
produces the same automorphism.
I'm not exchanging mark points at all. I'm simply
Right.
flipping these
You
two
are
edges.
flipping the two
Yes.
Because that's what you in the computation that you made,
Mhm.
you were switching the last 2 points, right, rather than the first 2. But this produces exactly the same automorphism.
Yeah.
You should leave infinity and A as they are, but switch 0 and 1. Right.
But isn't this correct? I mean, I'm switching A and infinity. I'm saying that if you tell me to put marked points at 0, 1,
But
yeah.
sorry, 0 and 1 were the 2 nodes, right?
No, sorry. So,
Okay, then it's okay.
Okay.
Yeah, so you are switching the nodes, in fact.
Yeah.
Okay.
yeah, good. Okay, I need to state the theorem, and then I would love to tell you one type of application. A theorem of Abramovich, Caparasso, and Payne works all of this out. So, I mean, I've been following the exposition of this paper quite closely. So the theorem is that the boundary complex of the toroidal embedding of Deligne-Mumford stacks is canonically identified with with the link, which we wrote delta GN. It's the cross section of tropical MGN, the moduli space of tropical curves. Okay. I would like to take 5 minutes to tell you an example of what good this does. So an application. I hope that's all right. Okay, so in some sense, boundary complexes have been around for a lot longer than tropical geometry has. Nevertheless, this is a rather useful shift in perspective, if nothing else, because it allows us to sort of make tropical / metric graph theoretical arguments to study this topological space. Now, why would it be interesting to study this topological space at all? I claim that it encodes some information about the cohomology of the space being compactified, in this case MGN. So the open space, not even the particular compactification. So let me just write some of this. So applications. So several facts. So suppose U in X is a compactification of some smooth variety. Over like some algebraically closed field, which is normal crossings. in other words, the boundary x minus u is normal crossings, then it is a fact that the homotopy type of the boundary complex u inside x is an invariant, so it depends only on u itself and not on the particular normal crossings compactification.
Is X smooth also?
Yeah, I think so. Okay, let me say that for now. Yeah. Yes. Okay, so it's an invariant of the space being compactified. It doesn't depend on the particular choice of normal crossings compactification. So it then becomes interesting to study this space as an invariant, right? Some combinatorial space associated to U. And that can be even, that can be made even stronger, that correspondence. So let's set K to be the complex numbers for the rest of the discussion. And I'll state that there is a weight filtration. This is Deligne's weight filtration. On the cohomology of U. And so let me just write it up to fixed notation. It's W sub 0 of H something U with rational coefficients up to W sub 2K H K U Q, which is the full thing. So, okay, so this is like some vector space. And I'm saying that there's like a canonical weight filtration on that vector space, so a sequence of increasing vector spaces that I won't define. And let me write GR, so the GRW sub K of Hj to be the relevant quotient. So this is the quotient of the weight K piece of Hj by the quotient of, by the weight K minus 1 piece of Hj. So this is like, right, this is just some vector space. And, so let me just write D for the dimension of the variety X. And then I claim that there is a identification, a canonical identification. Okay, what am I trying to say? I'm trying to say that the rational homology of this combinatorial space encodes top weight cohomology. So this combinatorial thing encodes like one slice in the sense of Deligne's weight filtration of the cohomology of the open space. So there's a canonical identification between the reduced rational homology of the boundary complex with rational, right, so rational coefficients, with the top weight, so weight 2D, which is the highest weight that can occur, cohomology up to a degree shift of U. Okay, and now it is in fact the case that this whole story works also for Deligne-Mumford stacks. And so the details are worked out in an appendix of a forthcoming paper with Galatius and Payne. And the point is that we can now study the top weight cohomology of MGN by doing graph theoretic computations on this boundary complex. Okay. So I'm yeah.
There the top weight was 2K, and there you have 2D. So for HK,
That's
it's
right.
2K.
But it's, yeah, so it's in fact the case that the top weight is always is always 2D.
2D minus I, wouldn't it be graded 2D minus I?
Okay, so this, I really mean top weight here. So it's in fact the case that the weights like vanish after 2D. Yes, so sorry, there's a lot of details that I'm suppressing. Okay, it's a combinatorial space that encodes top weight cohomology. Okay, I think, let me just refer you to a couple of forthcoming papers. So see a paper with Soren Galatius and Sam Payne, which in particular works out everything having to do with M1N. as well as some more general statements about boundary complexes of MGN and their combinatorics in topology. And I'll refer you also to a paper that has some computational results obtained essentially by computational and graph theoretic means on M2N. It's a companion paper. And I was hoping to take a few minutes to give you references to the many parts of tropical geometry that I just didn't have time to deal with in these 5 lectures. But I'm out of time, so what I'm going to do is I'll try to update the references in the notes that I posted, and I'll repost them. Okay, thanks for your attention.